So, our electron homes. Okay? In theory, we may have started a little bit further back, okay, because I don't remember exactly where we ended. We've got our energy levels, okay, which we can go through and name. Okay? What name do you want to call the first energy level? 1, because we're super creative and we picked numbers for names. Okay? Arguably a horrible system, but that's what we went through and did. Okay? So if we reference the first energy level, we call it energy level 1. That is its name. Don't associate any numerical value necessarily with it. Okay? When we place electrons, we would place our first electron lowest in energy first, closest to the nucleus. Okay? So if we were going to get kind of vague about it, we could just say, well, there's an electron. Okay? We could then say, well, electrons are going to repel each other. I'm only going to put 1 electron in. If I did that for each orbital, that would only give me 7 electrons. There's 118 elements. Okay? I need a lot more than 7 electrons. So one of the next arguments that could potentially come up is that we encounter something known as electron spin, okay, which is this weird quantum concept that you don't need to really stress about, except that electrons have spin, and as long as they spin opposite directions, they're allowed to be in the same orbital. Okay, so really that just means every orbital should have 2 electrons in it. So this now increases the amount of electrons I could fit into my electron home. So I can now get up to 14. I'm still drastically short. Okay. Again, back to the quantum mechanics and the probabilities of finding electrons. We find that every time we move up an energy level, a new orbital type appears. Okay. That orbital type is what we would refer to as a sublevel in the textbook. I would argue orbital type makes a little more sense. Okay, so every time we move up, we get a new one. Okay, we always copy the old one, but we now get a new one. So if we start at the first energy level, the orbital type we get looks like a sphere. If I move up to the second energy level, I have to copy the previous, okay, because I want to be able to build on it. So the first version of the second energy is going to look like a sphere. Now the new one on top of that becomes the dumbbell. When we go up to the third energy level, what happens? Sphere. I get a sphere, I get a dumbbell, and then, oof, close enough. I get what we would call a cloverleaf, okay, or what we're attempting to call a cloverleaf. Okay. This drastically, again, increases the amount of electrons that we could theoretically fit into our orbital system. Okay. It, again, doesn't account for all the electrons appropriately. Okay. Which is why we bring in the next concept of orbital orientation, which the word shows up on the slide, but I don't want to advance because I've got pictures. Okay. The orientation is in reference to those particular orbitals. If I take a sphere and I rotate it, I change its orientation, can you tell it was rotated? No, because spheres are perfectly symmetrical. Okay? So there's only one possible orientation for the sphere-type orbital. Okay? The dumbbell shape, however, if I rotate that, can you tell it was rotated? Yes. Okay? Because we can tell it was rotated, that's where we're getting this kind of concept of orientation. Okay? And it turns out that we get 3 orientations. We could refer to it as the y-axis, the x-axis, and then the one that is impossible to draw nicely, the z-axis. Okay? And we're kind of shading that because it's behind it. Okay? And there's our z-axis. Each of those is a new orbital. So if I was to go through and use kind of the line representation I've been working on, we have the first one, first energy level. Our second energy level splits into those 4 possible orbitals. I want to be able to name these. If I point to this bottom line, I don't want to say point to the bottom line because I have to point. Okay? So how can I name that orbital so that everybody knows without me pointing? Okay? What energy level is it? It's the first energy level. What orbital type is it? Sphere. That's a lot of words. Letters. I want to come up with an abbreviation. I'm going to call it 1S. Why S? Sure, let's go with sphere. Okay. If we move up to the second energy level, what's that one now called? The 2s, because it's the second energy level. There's only one orientation for it. It would also be a sphere, so it's 2s. How about the one above it? Okay. These are now 2 dumbbell. Dumbbell is, again, way too long of a word, so we come up with a new name for it or a new symbol. We call it P. Okay. How about the next one? It's still the second energy level. Okay. I'll get to that in a second. What's the last one? Also 2p. Okay, so there are 3 2p orbitals. Okay, because there's 3 orientations. If I want to get really nitpicky, I could go through and specify how they are different. How are they different from each other? X, Y, and Z axis. So I could refer to those as 2px, 2py, and 2pz. Why do I not want to bring in and say 2p, say 2? Let's put that in red. That upper right-hand corner is reserved for special information. What information do we place in the upper right-hand corner? It's charge. How do we determine charge? The electrons. So when we're looking at our electron configurations, what is reserved for the right-hand corner? The number of electrons in that orbital. Okay, so I don't want to call this 2p1, 2p2, 2p3 because that then confuses the notation I've already used. Make sense?
Isn't that kind of on the table too?
We'll get to that, yes. It is absolutely on the table. Okay. What happens when I move up to the third energy level? Where's that one? Okay. S isn't fully correct because I'm pointing here. This is also S. This is also S.
3s.
So it's 3s. Okay. The next one? 3p. Officially, again, 3 of them. The next one? 3d. Okay. We'll talk about the orientations for that one in a little bit. Okay. So all of this detail is now getting kind of added in because what I want to be able to do is now reference where every single electron goes in an individual atom. So if I want to look at, say, hydrogen. Hydrogen has how many electrons? Rhymes with fun. 1. It has 1 electron. Where does that 1 electron go? It's going to go to the lowest energy orbital. The lowest energy orbital is the 1s orbital. So I can say I have placed an electron in the 1s orbital. How many electrons did I place there? 1. So I will call it 1s 1. What happens if I move to helium? Okay. 1s, the first electron goes into the 1s. Where's the next electron go? Also into the 1s. Okay. That's going to be a bit tedious to have to string that out every single time, specify the exact location of every single one. How do I condense that? 1s2. Okay? So we're just trying to shrink the electron configuration so that it takes up less space. Okay? So now let's take a look at a couple quick patterns here. Not beryllium. Let's try that again. Let's try lithium, sodium, potassium. Lithium, first electron. 1s1, second electron. It's also going into the 1s. Okay, remember, this is why we have the drawing set up here. The first electron goes here. Where's the second electron go? If I go to the 2s, what have I left? An empty hole where I could have placed an electron. The electrons will fill lowest energy first. Remember, every orbital holds 2 electrons. Okay. This gets tedious, so what do we skip to? 1s2. Where's the next electron go? Now we move up to the 2s. Okay. I'm placing 1 electron there. Where's the next electron go? Ooh, good catch. There are no more electrons. For lithium, there's a total of 3 when it's neutral. So that's its electron configuration. Sodium.
2s2.
Okay. Dealing with the numbers, we might be trying to jump in. Okay. We've got it drawn up here. We go 1s, 2s, followed by 2p. It's right there. We just read right off. Okay. If I did 2p1, would that get me to sodium? No. 2p2, 3, 4, 5, 6, and I can call it 2p6. I could break that down as 2px2, 2py2, 2pz2. How many people want to do that? No. Good. So we just say all in the p orbital, I fit 6. Done. Okay. Can I fit more than 6? No. Yeah. How many orientations are there for a p orbital? 3. Each orientation holds how many electrons? 2. Can I fit more than 6? No. I'm capped at 6 electrons in the 2p. Have I achieved sodium yet? No. So what do I need to do? I'll move to the next orbital, which is 3s1. No more electrons because I've achieved sodium. Okay. Potassium. It's going to end with 4s1. You might say, well, Mike just knows that because he memorized it. Didn't actually memorize it. The periodic table has this information stashed in it. Okay? Which row was lithium in?
2s.
2. Right? Which row was sodium in?
3.
Which row was potassium in?
4.
Okay? The energy levels are specified based off of where they are as far as rows in the periodic table. Okay? The next part gets a little bit tricky. I'd have to specify those s's. How do I know it's s? How many electrons fit in the s orbital type? 2. How many columns do we see starting our periodic table off with? 2. Guess what orbital type those 2 columns always end with? S. Okay? So because potassium is in those first 2 columns, that has to be an s-type orbital. How do I know it only has 1 electron and not 2? Which column is it in? It's in the first column of it. Guess what? It has 1 electron. What about the rest of the electron configuration? Okay, it's full. I could max it out. There's 2 ways to go through and do that max out. One is going through 1s2, 2s2, 2p6, 3s2, 3p6. Okay. We'd evaluate all of those pieces, okay, and we drop them all in there. A hand gesture was made probably in reference to the shorthand version of that. Okay. Everything in blue corresponds to what element? Which one are we looking at? Okay. That corresponds to argon. So what I can do, for my electron configuration is say potassium is the same as argon plus an electron in the 4s1, or a 4s orbital. Done. Okay? Kind of, sort of? Okay. And I know you probably want some more practice on this, and we'll do a little bit, but not a whole lot. Okay? So the next part, what do you think the configuration for strontium is going to end with? Okay, so I don't want its a whole electron configuration, I just want it what it ends with. Strontium is SR, yep. It is not in the 4th row, it's in the 5th row. Its first 2 columns are the S-type orbital. Second column of it, 5s2. Everything before that is full. Okay? As far as everything before it being full, we could cheat and use Kr, okay, as our electron configuration there. Sometimes you see the shorthand, sometimes you don't. Okay? When it comes to this class, and we'll address a couple things, typically what we're testing on for the electron configuration is the end of it. Okay? And we'll talk about why we care about the end of it in just a second. Okay? So if you can first zero in on what that last orbital is supposed to look like, that can probably eliminate most of your answer choices. Okay? The rest of it might be looking at the nuances of what's happening in between. Kind of, sort of makes sense?
So it's always going to be the noble gas in the period above it, right?
The shorthand version is always the noble gas from the period above it. Okay, always. It is never, I can't say strontium is, so this is not acceptable. Rubidium plus an extra electron. No. It has to be a full satisfied orbital set, and in particular, it has to be a noble gas. Rubidium's not a noble gas, I can't use this configuration. Okay, it has to be a noble gas. Okay?
So if we're taking an exam, is it going to be both ways to
So
answer?
on the exam, because most people seem to not like the shorthand, you'll get the longhand. Okay? The next part with the longhand is, again, a quick check for this. Okay? What did we say the superscript was? The number of electrons, right? Or it's ultimately where our charge is, but that's dictated by electrons. So in the electron configuration, we're only looking at electrons, so it's just the number of electrons. What is 2 plus 2? Plus 6? Plus 2? Plus 6?
18.
Plus 1?
19.
What was the atomic number for potassium? 19. Add up your superscripts and you have the number of electrons for that element. Okay? Those are the two simplest and easiest ways to eliminate answers. In my experience, it's either changing that end part so that it's something wrong, or you've messed up something through the numbering in between where it doesn't total up right. Okay, after that, you have to get deeper into the woods. Like maybe it says 3p7. Can it be 3p7? Why not? It can only hold 6 electrons. Okay? Kind of, sort of? Okay. As far as electron configurations and what you guys are responsible for, you're looking all the way through argon. So there's 18 practice questions. Determine their electron configurations. Okay. You want more? There's another 118 elements. Okay. But we're going to run into some complexities the further through the periodic table we get. Okay. For instance, when we looked at potassium, we started with the first, right? 1s. Then where did we fill? 2s. Then what did we fill? 2p. Then what did we fill? 3s. Then what did we fill? Then what did we fill?
4s.
What happened to the 3d orbital? Okay. So we get a couple answers on this. One, it comes after. How do you know it comes after? And you did an awesome job pointing to the periodic table. The periodic table tells you it comes after. Okay, the first two columns were our S block. Guess where the D block is? Scandium to zinc. Scandium to zinc is filling in your d orbitals. Right? So if we filled from magnesium, magnesium was 3s, aluminum is third energy level, p-type. How do I know it's p-type? It's in a different section of the periodic table, a different block, a different rectangular square. How many electrons could I fit into the p orbitals? 6. How many columns are there in the p block? Neat. Okay. No, there's 6. Okay. It's okay. I have trouble counting 2 sometimes. Okay. What happens after argon? Where do we move to? It's like, well, it should go to the D. What's the next element that I go to? I'm in the S block. The periodic table tells me the fill pattern. Okay. The next fun question that would come out of this is, why did it do that? Right? Or are you just accepting it? Just accepting it. At least you're honest. That's okay.
Why is it 3D not 4?
We'll address that too. There's our 4s. I'm showing it in orange so it shows up. What is the difference in energy between the 4s and our 3ds?
It's closer. Lower energy.
They are darn close to each other. Okay? It is not a lower energy level because it's 4th energy level versus 3rd energy level. Okay? So why would we go up in energy? Okay? Our second electron went into the 1s orbital, not into the 2s. Okay? Why did we not go to the 2s? There was a lower energy state. Okay? So why, when I fill and get up to now 3D 4s, why does it not fill 3D and it fills 4s instead? Okay? I really like this. This is kind of fun. Let's make a comparison here. Here's our 4s with a single electron in it. Okay? 3D, we didn't talk about the orientations. Any guesses how many orientations? 2, 4, 10, we're all wrong. There are 5 orientations. How would we know there's 5 orientations? The first 2 columns were the S, right? Okay. Far right, we had 6 columns, which were the P. That makes scandium to zinc D. How many columns are there in the D block? There are 10 columns. Every orbital can hold 2 electrons. So there's my 5. Okay? I don't have to memorize how many orientations there are as long as I know how to interpret the periodic table. That can be a big leap, but the periodic table has it. Okay? So there are 5 orientations for the D. 1, 2, 3, 4, 5. There's our 3D. There's our first electron. Visually, which of those looks better to you? Orange or green?
Orange.
That's actually interesting. I've never asked that question before. I was just curious. Everybody said 4S. Why do you say 4S? Why is that visually more pleasing than 3D?
It's complete. It's balanced.
It's not complete because it's not full.
No, you're right. It does look more balanced.
It does look more balanced. There's a symmetry associated with it. It looks aesthetically pleasing. Okay? The analogy that I usually like to use, we'll go through it kind of fast, is if you envision the most attractive person you're aware of. Okay? And this is usually where I tell people to stop staring at me because it's very nerve-wracking. Okay? As you're like making eye contact, thanks. Okay? And you mirror the left side of the face to the right side. And you might have seen internet meme things about this. What you will find is people that are classically determined to be attractive, you can't tell that you mirrored their face. Okay? You could look it up. They've actually done studies on it. The most attractive person, I think, was somewhere in Scandinavia, okay, by whatever arbitrary statistics that people use. Okay? And they mirrored her face across, perfectly symmetrical. You think about all the famous actors and things like that, the ones that really climb to the top have very symmetric faces. There's usually something that's just slightly off, because when you think about like perfect people, you're like, oh, I don't like you because you're perfect. Okay? Same deal with superheroes. We don't like superheroes that are perfect. We want some flaw in them. Now they got a peg leg, so now they're cooler because they have to fight with a peg leg. Okay? There's some kind of internal struggle, some slight asymmetry. But we're still focused in on that symmetry. Guess what chemistry does? The exact same thing. Why is that symmetry thing not showing up earlier? There's a difference in energy. It's only showing up when the difference in energy becomes relatively small. Symmetry is a very small contributor to the overall balance of your structure, which is why it only plays a role when the orbital energies get close enough that that now becomes important. Okay? It's a really neat phenomenon, in my opinion. Does it keep coming back? Yes. Pretty much the rest of the periodic table has all sorts of symmetry issues with their electron configurations, which is why I tell you to stop at argon, and ultimately calcium is fine. Okay? But as soon as we bring in the d orbitals, everything goes a bit haywire, and you have to be a little bit more careful with how you fill your orbitals. Okay? Because you have to start thinking about symmetry effects. Okay? Or you just look at the periodic table and trust someone put it together right. Okay? And you just use it. Okay? To that extent, let's go ahead and take a look at scandium. Where is scandium's last electron? It's going to be in the d orbital because it's part of the d block. So we'd probably call it D1 because there's 1 electron there. What's its energy level? I'm being a jerk.
But it's
in the 4th row, but it's 3D. Why did we offset it? so that it matches the fill patterns. Okay? If we shifted scandium up, it doesn't match the fill patterns. Okay? So we had to shift it down so that our periodic table helps us with how we place electrons into it. That's why it's offset. So you have to remember that the d orbitals start at the third energy level. Okay? Which, if you remember how we generated the new orbitals, you would know that. Okay? Kind of makes sense? Okay.
Would that be 3D1 right there?
Scandium is 3D1.
And
Titanium would be
3D2?
3D2. Okay. Just to be extra obnoxious, cerium, I think I'm right.
That would be
Ooh, it's a new block.
4F2.
So it's not S, it's not P, it's not D,
It's F.
it's F. F is the new name that we go through and use because we ran out of Fs. Sorry. Different teacher. So F is our new block. How many orientations for our F block? We have to be careful. These first two don't count. They're actually embedded up here. How many orientations for the F orbitals? 14 electrons, 7 orientations. Okay? So cerium being, I'm assuming it's cerium. Does someone want to challenge me on that? Or tell me I'm right?
You're right.
CE, I think I'm right.
I don't know. Are you right?
Yeah, cool. There we go. So cerium. Right? What would its last electron be?
4F1.
It's F1. Why is it 4F1? Because if we look where it's coming from, it's coming in here, which is right the 6th energy level, right? Why is it coming in at 4? It was offset because of the d orbitals, and now it's offset because of the f orbitals. It's a double offset. You have to remember that. Okay? Sort of. You don't have to remember that because why would I ever ask you anything about that? Okay? All of those are radioactive elements. You will never, well, maybe one of you, maybe, would deal with radioactive elements. In fact, I think someone in here worked on a nuclear sub. You probably dealt with some of those. Right? Most people won't, so we don't need to worry about those. Kind of, sort of?
Kind of, sort of.
Okay. So there's, see, I told you, orbital orientation. The word just appeared, but I had all those drawings. Okay. A lot of people get bogged down and confused by this. This is no different than your address. Okay. Your address, you have to tell people the state that you're in, the city, street, okay, the number on that street. What we're doing here is the same thing. You're just defining the location for the electron. You have to memorize how that address system works. It's a new address system, so it takes some practice, but that's all it is.
You're basically saying their coordinates to the last one.
Yep. And ultimately, remember, your electron configuration specifies the coordinates for every single electron.
You can't
Okay.
just put like
The
P2 in the end, you have to put like
You have to do the whole thing. Yep. So the biggest place for students to make mistakes is in the whole thing. So people usually don't see what's happening at the very end. The most important part is the very end. That's the last electron. Okay? And we'll talk here in a second about why that last electron is the most important. So if you start there based off of your coordinate planes and just fill everything else in, you're fine. Okay? So if you keep your focus there, that's helpful. You still need everything. Okay?
What about the octet row? How is that?
Don't worry about that yet. Okay, we'll get there. Orbital types. We just addressed all of our orbital types. We have sphere, dumbbell, cloverleaf. Okay? The sphere, when we rotate it, there's only one orientation, so we don't have to worry about it. Okay? Sorry, I didn't think it was going to do that. The dumbbell, I get 3 orientations. Okay? X, Y, Z. For the cloverleaf, that's my d orbital. I get 5 orientations. Okay? Does that look like a cloverleaf? No, what does it look like?
Pacifier.
It's kind of a kinky pacifier, right? Yeah. Sorry. For twins? Losing focus. Okay. This looks an awful lot like a dumbbell with a belt. That's one way to look at it. It's usually described as a dumbbell with a donut. Okay. So you get the dumbbell donut shape. Okay. Not a big deal, just something to kind of consider and realize the names that we picked for these were kind of arbitrary. The orientations, as I'm phrasing them, are also arbitrary orientations. It works really well for the s and the p. It fails miserably for the d orbitals. Okay? Why do we talk about it as an orientation then? How many of you can understand the s orbital has only one orientation? The p orbital has 3 orientations? Okay. Why do you understand that? Take a sphere and we rotate it. What happens? Oh, I can't tell. Take a dumbbell, I rotate it. Oh, I can tell it happens. Okay. We can visually see those orientations a little bit better. Why does it fall apart with the clover leaves? How are those last 2 different orientations of the same thing? They aren't. Okay? And that's because orientation isn't true. Okay? What it's coming down to is the quantum mechanical solve for how an electron can exist. Okay? Which is really fancy gibberish for saying you don't want to know. You accept it. Okay? The orientation is nice and simple, and for the sake of Chem 130, it's phenomenal because it can help us see what's going on with that. And for our Chem 130, I said we stop at calcium. What orbitals do we fill? S and P. Keeps it simple. We don't have to worry about the weirdness happening in the D. 151, do you need to worry about the weirdness potentially with the D? Yes. Okay? But even then, they don't get into the quantum mechanical solve. Okay? I've probably taken more quantum mechanics classes than any faculty member here, and I understand probably less than any faculty here when it comes to the quantum mechanics. Okay? It is a beautiful system, but it's a lot more complicated than we could ever potentially give it justice. Okay? This is just kind of a fun thing to go through and address. Energy level. The sublevel, I have just the s orbital. How many electrons fit in that sublevel? 2. So the total electrons for the first energy level? 2. Okay. What happens if I move to the second energy level? I would have 2s. I copy the previous, so I have an s. And I also have a 2p. How many electrons fit in the 2s? 2. How many electrons fit in the 2p? 6. Good answer. Okay. A single 2p orbital holds 2 electrons, but the 2p sublevel holds 6 because there's 3 orientations, so that means 3 orbitals. Which means for the second energy level, how many electrons do I fit? 8. Remember again, I said we go up to calcium for our electron configurations, and we kind of ignore that. Okay, which means we maximally fill out pretty much, and actually if we continue this, we could go through and do 3s, that would be a 3p, 3d, 2 electrons, 6 electrons, 10 electrons, trust me, that's what those things say. Okay, and we could even do the 4s, the 4, yada, 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 yada. Okay, calcium came in at the 4, but I'm only concerned about the s and p. Okay, calcium skipped D and went to 4s, which means maximally in an energy level, how many electrons am I concerned about seeing? Only counting the s and p's. 8. What was your question? Octet rule. The octet comes because when we fill just the s and p's, we get our 8 electrons. That's where we make reference to the octet rule. Okay? So there's all those things. Electrons, total it up. We can look at it pretty, yay, good. Okay. We just drew all this out on the previous slide, so I don't want to redo it. Electrons are added into our orbitals. Okay? Lowest energy first, pair before finding a new orbital. Okay? This pairing before finding a new orbital will be an interesting question that we'll talk about when we talk about ionization energy in the next unit, the beginning of the next unit. Okay, so just kind of remember that. Okay. You can see reference to this filling diagram, okay, which is awesome. Some people are like, oh, that's greatest. Okay, I just write it all out and then I just kind of, sew my way through and it tells me the electron filling. Every time I've used that, I've somehow, and I don't know how, I've shuffled all the orbitals. Which then means when I go through to sew it, I go 1s, 2p, 3s, 2s, 3p, 5s, what? And I'm lost. The periodic table tells you the fill pattern. Okay? You don't need this thing to do it. If you want to use it, you can. The easiest way to set this up, as best I can tell for why I always screw it up, which if you watch me write long things, what happens is I write long things. I stop going linear. You have to be very linear here. What we're looking at is a grid pattern. Okay? So if you do this in a grid, you're awesome, you got it. If you write like me, you're going to fail at it every single time. Use the periodic table. Okay? The next big thing that comes out for electron configurations gets us some information about chemical properties, and this is valence electrons. Okay? So let's pick a really, 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 really simple one. Hydrogen. What is hydrogen's electron configuration? 1s1. If hydrogen is now going to interact with another thing in the environment, I don't care what that thing is, what is the first thing that hydrogen owns that is going to interact with that outside environment? The electron, not the proton. Why not the proton? The proton's in the middle, and it's a marble inside the superdome. Okay? So the nucleus is insanely tiny, not going to interact with our outside world to a first approximation. We're concerned about the electron. So that makes sense. So let's move to the next one. Let's look at carbon. Carbon's electron configuration, if we try it in the reverse order that we talked about, okay, it's in the second row, so the last orbital filled will be in the second energy level. It's in the p block, we'll get to that. 2p, it's in the second column of the p block, so it becomes 2p2. Everything before it fills, unfortunately I've got all that memorized, 1s2, 2s2. Okay. With a little bit of practice, you'll pick that up. And we now have the electron configuration for carbon. What makes carbon more difficult than hydrogen? There's more electrons. Okay. Which electrons are going to interact with the outside environment first? Okay. We would reference the highest energy electrons. Where are highest energy electrons? The last. Okay, that's not bad. Unfortunately, that's not clear enough. The next clear answer was 2p. I'm going to argue p has nothing to do with energy. What part of 2p2 has to do with energy? The 2 in front. Because what did the 2 in front represent? The energy level. Okay? The p was the type of orbital at that energy level. The 2 was how many electrons there were. So if I'm concerned about the highest energy electrons, where should I be looking? The highest energy level. Is the 2p the only highest energy level? No. What else is there? The 2s. So I'm going to look for the highest energy level electrons. So I'm looking for that first number. How many electrons are in the 2s? 2. How many electrons are in the 2p? 2. When I add those two up, what do I get? 4. How many valence electrons does carbon have? 4. Okay.
That's written.
What?
That's written on there.
We'll get there, yes.
So to make it easier, don't you just want to...
We'll get there, we'll get there. Oxygen, 1s2, 2s2. I know, you guys want to jump. Because I think I already gave you the cheat in the thing. And then oxygen, 2p4. Yeah. How many valence electrons does oxygen have?
6.
2 and 2. 2 plus 4 gets me 6. So there it is. I've got it. So I can use the electron configurations. The periodic table is so awesome in its organization, it also already tells you those electron configurations. Or not the electron configurations, the valence electrons. The valence electrons are arguably the most important because they're the ones interacting with the outside environment. So I want to be able to find them as fast as possible. Is writing out an electron configuration particularly fast? No. No. So I want to be able to look at the periodic table and be, there it is. So let's take a look at carbon. Okay. Carbon, there's two numbers written above that column, right? 14 and then IV. What the heck is IV?
4.
The Roman numerals 4. 4. That was kind of silly. 4. Okay. How many valence electrons did it have?
4.
4. Oxygen.
16.
And what are the Roman numerals for? 6. The Roman numerals literally tell me the valence electrons for every element in that column. Why do I know every element in that column has that same valence electron count? That's the way the periodic table is organized. Mendeleev organized them according to groups and families. And within a group and family, we said the chemical properties are the same. When we're talking about valence electrons, we're talking about chemical properties. That's why they have the same valence electrons. It's in the count. Okay, kind of makes sense? Okay. Did you actually have a question, or are you going to answer my question? Okay. Sorry, I'm kind of talking over everybody. What's the deal with the 16, the larger numbers? 16.
That's the root.
Okay.
Or the family.
We could reference that as the family number 16. That doesn't really get us our 6. But isn't 10 minus 16 6? Yeah. Isn't 14 minus 10 4? What would boron's valence electrons be? 3. Isn't 13 minus 10 3? Minus 10, an awful lot. Why am I minusing 10?
That's the transition group.
The D block is numbered in there. All we're subtracting out is the D block. How many electrons fit in the D block? 10. So if you just subtract 10, ignoring the D blocks, you've got it set. How many valence electrons for strontium, SR? 2. Kind of make sense? Yeah? Cool. What?
Wait, how would you find valence electrons for D?
How would you find the valence for D is a perfectly awesome and valid question that I'm not going to answer because we aren't going to worry about it. You can talk to me after class if you would like more details on that. Okay? So our periodic table is pretty awesome because of that organization. The first two columns get us S. Then we get the D block, the P block, and the F block. You will notice that helium appears to be located in the P block. Okay? But in this organization, they've highlighted it red, meaning it's S. Okay? That first energy level is exceptionally anomalous, and it doesn't quite fit within our periodic table appropriately. So if you look at the large periodic tables in the tutoring center, because you've been visiting that and getting help with science, good job, you will notice those two elements are actually offset from the periodic table. Okay? Because we can't use the patternings quite as nicely for those two elements with the rest of their counterparts underneath them. Sometimes it works, sometimes it doesn't. Okay? That's why hydrogen and helium sometimes show weird things on the periodic table. Okay? We'll see. Okay? So, our atomic radius. Actually, here. Let's just look at the last two. Why does the atomic radius increase down a column? We now have the knowledge. Remember, we started this whole thing off with what's the trend in radius? And down a column, what was our initial statement? It's bigger because more electrons. Okay? But it decreases from left to right. And left to right, what's also happening? More electrons. So why is that rule not explaining both systems? Okay? The reason the rule wasn't explaining it was because we didn't know where our electrons exist. Do we know where our electrons exist now? Yes. So let's use that information. Down a column, what happens to the last electron? So lithium's electron configuration was what? Last electron. 2s1. Sodium? Rubidium? 5s1. I was being kind of annoying there, but not intentionally. That's just the way it was written. Rubidium's a little bit lower than potassium. Cesium? 6s1. Why would I get larger down a column? What's happening to that last electron? It's being placed at a higher energy level, which means It's further from the nucleus. Okay? The larger the energy level, the further from the nucleus it gets. That's the pattern we're seeing. It's not more electrons, it's that the last electron goes in at the higher energy level. So it's all about where the electron's getting placed. Yes? Nope, it decreases. And absolutely you have to memorize it decreases left to right. It does not increase. Okay? And that becomes the tricky part. Left to right, we would think it should increase because there's more electrons. Okay? Because we look at the column and we say, well, it has more electrons, so it should get bigger. Okay? It's not that it has more electrons, it's the electrons are going in at a higher energy level. I'm concerned about where that last electron is located. Okay? When we move to the next one, atomic radius decrease from left to right. Okay, so let's look. We've got lithium. Lithium? Yeah, let's do lithium. Oh, I can't do that. We're going to do it this way. I'm going to have to rewrite it. Lithium, the last electron was, I already forgot, 2s1. Where's carbon's last electron? 4 would be referencing the number of electrons. 2 is referencing the number of electrons. Where's the last electron go? Just 2p. That's it. 2p2 is now saying there's 2 electrons. I just wanted the last one. The last one goes into the 2p. Neon. Where's its last electron go? It's 2p. So far, so okay? And again, it's the question that I'm asking. I'm not asking for the entire configuration. I just want to know where the last electron goes. Okay? Why is this important? 2p versus 2p. Which one's higher in energy? They're the same. 2p versus 2s, which is higher in energy? They're the same energy level. Which means when I go left to right on the periodic table, where's the electron going? The exact same distance from the nucleus. That means there is no change to the radius. Because it's not going to a higher energy level. It's not going to a lower energy level. It's going the exact same place. If it goes to the same energy level, okay, what happens? No change in radius. Everybody okay with that? Does that say no change in radius? What else is going on?
More protons.
When we change across the periodic table, thank you. Oh, yeah, it's still happening. Lithium to neon, what else is changing? Lithium has how many protons? 3. Neon has 10. Okay. Our protons and electrons are effectively magnets because they're attracted to each other, much like a north and south end. I take 2 magnets and I line them up so they just don't interact, so they don't quite suck together. Okay? Now I make one of those magnets stronger. What happens? It pulls it in. What happens when we go left to right on the periodic table? I'm making that magnet stronger by giving it more protons. The electrons, because they're coming in at the same energy level, and now the nucleus is becoming stronger, get sucked in just a little bit. Which means when we move left to right, we see the decrease in the period. Okay? Kind of makes sense? It's tricky, but that's what's going on with it. Okay? And just to back it up, just in case you were curious, because maybe I misspoke before. 0.08 is boron. Fluorine is 0.064. It is indeed smaller. Okay? If for whatever reason you decide to continue through chemistry, awesome, good for you. Come back and see me again when we get to OChem, and I'll add and change that rule. Okay? That is officially true, but in OChem we don't like truth, so we change it. Just kind of unfortunately true. Okay? Electronegativity, it is not directly talked about in your textbook. Okay? But what electronegativity is the ability for any atom to attract bonding electrons. Okay? It is very specific. It is bonding electrons. Okay? So what Linus Pauling, I'm pretty sure, went through and did is he attempted to measure and quantify that ability to pull electrons in. and he came up with a table and listed the electronegativity for all of these elements. And what he noted was that fluorine had the highest electronegativity. And he noted that cesium has the least. And he said, you know what? On a general trend, electronegativity increases up a column and left to right. Okay? That in and of itself isn't a big deal, except what he did with that is then use that information to explain bonding patterns. So now we have structures. Once we have structures and we overlay electronegativity on it, we say, well, how do those structures interact with each other? They interact because of electronegativity. Right? So it is a massively important topic. It's talking about how electrons distribute through a molecule. Right? So it is critical in our ability to build Lewis structures. Yes?
Why do the last row and column don't matter?
Why did we ignore the last column? Okay. They're noble gases. They aren't going to react. There's no need for them to attract electrons. Right? If we look at this fluorine, okay, how many of you would like to win $1 billion? Like, I got $1 billion here. I'm just going to give you $1 billion for existing.
Yeah.
Right? Like 4 of you. Wow, that was amazing. The rest of you are like, there must be a catch.
I want to suck it.
No. $1 billion. Here you go. We're probably all going to accept that. Okay? Because then we get to be rich. Okay? We get to buy things. We get to show off all our wealth. Because if you had $1 billion, you don't live on the streets. You buy the coolest house on the block. You buy the coolest car. Okay? And everything's great and grand. You effectively become a king or queen, right? You'd become the nobility. What is happening with all of our elements? They all want to become the nobility. It's now just a question of how they do it. If I take a look at fluorine and compare it to, it's because it's angled, neon is actually closer to it, right? Fluorine to neon. What is the difference between fluorine and neon? As a hint, there's 2 things, 3 things. 1 we can ignore. Fluorine and neon.
Fluorine has 7 valence electrons.
Fluorine has 9 electrons. We'll get to the 7 later. And neon has 10. What else is different? What's that?
7 and 8.
If we look at valence, so let's ignore valence for the moment. Fluorine has 9 electrons. Neon has 10 electrons. What else is different between them? Yeah, the rows, though, reference kind of our electron count. So it's kind of saying the same thing, but acknowledging a different way to interpret it. We could look at electronegativity. Keep going. What contributes to atomic weight? Neutrons and protons. Neutrons just contribute to mass, so really, who cares? Okay? You're probably not like, oh, I weigh the exact same as Kim Kardashian, so that makes me famous. That doesn't really work, right? Okay? But if I change the protons, what happens to my identity? It changes. I would become Kim Kardashian. Now I'm famous. Okay? But I can't do that because I lose my identity. So I can't change the number of protons because then I'm no longer me. So what do I change to become like Kim Kardashian? I don't know why her name came up first, but it did. So we're dealing with it.
The electron.
I could change the electrons because the electrons don't change my identity, but it changes my charge. Okay? What was special about our noble gases? Well, they didn't interact. How many of you know Kim Kardashian?
Like personally?
Yeah. Not, yeah, let's just, yeah, personally. Let's just stick with personally. Okay? Okay, why not? She's rich, bodyguards chase people away. Okay? We're poor suckers that can't deal with them. Okay? Same deal's happening with the noble gases. Okay? They're that nobility. Everybody wants to look like them. We can't change our number of protons because then we're not who we are. What can we change? We can change the amount of electrons. Okay? What does fluorine have to do to look like neon? Gain 1 electron. Okay? As opposed to boron, what does boron have to do? You're right, I was going to say 6. Gain 5 electrons. Which is easier to do? Gain 1. So boron's like, that's a little difficult for me. I'm probably not, I might be able to grab 1 electron, but the odds I'm going to pull 5 isn't so likely. Fluorine's like, all I need is 1, give it. What did it just do? It stole those electrons from another atom. Its electronegativity is really, really high because it is very easy for it to bridge that gap. Okay? So the higher the electronegativity, the higher its ability to grab those electrons. That's what's happening there. Okay? Fluorine could gain 1 to look like neon. What would oxygen need to do? Gain 2. So if I was going to look at, say, charges for these elements, the ionic charges, isoelectron, okay, same electrons. Fluorine needed to gain 1 electron to look like neon, and it would become a -1 charge. Why? It gained an electron. What happens to oxygen? Gains 2. Nitrogen? Gains 3. Chlorine? Gains 1 to look like argon. Sulfur? 2. Phosphorus? 3. Aluminum? Loses 3. But we only talked about gaining. Why is it now losing 3 electrons? What is aluminum trying to look like? Neon. We're trying to look like whichever noble gas is closest to us. Fluorine isn't trying to look like xenon and gain, I can't do that math, 43 electrons. Whatever, number of electrons. It's not doing it. It's trying to look like the closest one, which is neon. That's why it only gains 1 electron. Okay? When we look at aluminum, we're still thinking kind of in this linear fashion. Argon's the closest. Okay? The periodic table isn't linear. Loop it back on itself. And when you loop it back on itself, aluminum with 13 electrons in comparison to argon with 18, what would it have to do? Gain 5. What about neon? Lose 3. Which is easier? Lose 3. It prefers to look like neon, so it gains a +3. Okay? If we shift all the way to magnesium and sodium, what do they end up doing? Okay. Adding? Losing electrons. And this is one of the things that's confusing, is you're like, whoa, they're positive, so they must be adding. What are we losing and gaining? Electrons, which are negatively charged. Remember how I said that negative sign is going to be the bane of your existence? There it is. Okay? And this is just a simple example of it. Okay? Why is carbon disappearing from this? If we look at specifically the column where carbon is, it could either lose 4 electrons to look like helium or gain 4 to look like neon. Well, which does it do? Both. Depending on its system, it has charges that actually span from -4 to +4. How would you know which one it was? You'd have to do a bunch of extra work. Do you want to do that bunch of extra work right now? No. So what you want is to do the simplest and quickest things possible. So we tell you these charges and we say you need to memorize these. Why? These charges don't change. They will always be this charge. Okay? And I did see the slide picture. You're not going to want that picture yet. Okay, I'll make some adjustments in a second. There was first a hand in front. You still have it?
How come carbon can do both, but like tin says +4?
So we do end up getting some things that, of course, always fall out of the patterns we try and point at. Okay? And the big argument I'm going to come through, you shouldn't memorize these two. Okay? This is why I said hold off on the pictures. Why? Their charges are variable. Their most common charges are +4, but they do have some variability associated with them. We don't want to memorize them.
So you don't want to memorize that column +4.
Yeah. Okay. There are some elements that, for whatever reason, the textbook decided to omit from this. Okay. Those elements, connect. Those elements would be zinc, cadmium, and silver. You need to know their charges. Why might they be extra tricky? They're d orbitals. Okay? The ionic charges have other kind of rules applying to them with symmetry. The d orbitals are all about symmetry and how they apply, which makes assigning charges to those a lot trickier. Okay? Hence, most of it's 151. Except for those three, we require you to memorize those. Zinc is a +2. What do you think cadmium is? Why is it also a +2? Same family. Okay? Silver, it's a +1. Okay? Everything that is now up there, and I don't know why they emit beryllium. I always mean to look that up to figure out why they emit it. Okay? Part of that family, leave it as a +2, and you're good. You should have all of those memorized. So remember the note cards where we said name and symbol? You got some elements you should throw charges on. Okay, because you're required to know those charges. Okay? Again, should you memorize them? I would argue aluminum, zinc, cadmium, silver should be memorized. None of the others should be memorized. Why? You have the periodic table. You know what's happening. They're trying to look like a noble gas. You can just derive it. Okay? Last trick on this before we actually look at Lewis structure. You can memorize it for the first 5 minutes of the exam. Because when you get to the exam, you can write +1, +2, -3, -2, -1. Write in the +3s for, I can't point to it, but then write in for those elements as well. Now you can forget it because anytime you see it on the exam, all you can do is flip back to the front of the exam where you wrote the information down. You're done.
Question to be asked is what, like, when you would ask, what are the charges?
So how could the question get asked? At this stage, it would be what would be the charge for nitrogen? Okay. What would be the charge for oxygen? What we will find very quickly when we move into nomenclature, which, by the way, is an excitingly long video, just like Lewis structure, about an hour, that will be due next Tuesday. Okay? You can't find it yet. I don't want you to see it yet because I don't want you worrying about it. Do the exam. Okay? After the exam, you can move to that video. The charges rear their nasty head again. Okay? Questions? Okay. Chapter 4, these are in the slides. This just summarizes everything from Chapter 4 that you should know. Summarizes everything from Chapter 5. I forgot to make an edit here. We are not talking about ionization energy, so don't worry about it right now. Okay. Types of bonds. We get ionic bonds and we get covalent bonds. Ionic are metal and nonmetal. Covalent, two nonmetals. Okay, that's all we're dealing with at this point. Okay, keeping it as simple as we can. Okay. In the ionic bonds, again, metals will carry a positive charge. The nonmetals will carry a negative charge. Why? If we go back to our electronegativities, all of our metals have low electronegativities. All of our nonmetals have high electronegativities, which means the nonmetal will suck the electrons away, making it negative and making the metal positive. Okay, so it's applying that knowledge from electronegativity. This is where we hit this massive rule set for Lewis structure. Your textbook has a different set of rules. Okay? It is a different set of rules that irritates me every time I see it or have students use it. Okay? I will help you as best I can if you want to use those rules. They are horrible. Okay? But I will still help you if you want to use those rules or a different rule set that you found. These rules work for OChem. That's why I put them out here. Okay? Because if you follow a different set of rules, I have to reteach you Lewis structure when we get to OChem, and that's insanely frustrating. Okay? So, valence electrons is our number one thing. We need to know those. We need a central atom. Okay? That central atom, deciding what it is usually the least electronegative. Okay? Why? Because the central atom is probably connected to a bunch of other elements. Okay? Well, that means it has to be sharing electrons with a bunch of other elements. If it was the most electronegative atom in the middle, what happens? It gives up more electrons. Okay? That's opposite of what electronegativity means. We add electrons in pairs to the most electronegative atom first. That is the biggest differentiator, right there. You add them to the most electronegative. Not the outside, not the inside, the most electronegative, wherever it shows up. Okay? You'll continue adding electrons in pairs until the total electrons are accounted for. Okay? Anywhere you have pairs of electrons between atoms, you turn into a line. Rule 6 is where things go completely sideways. Okay? After you have a Lewis structure, you can then go through and evaluate shape, and that's what this chart is. Do you have to memorize this chart? Yes. Okay? It really isn't that bad. If you have one group of electrons, that means I have two atoms with one bond between them. What is that shape going to be?
Line.
Linear. It's a line. There isn't a choice. If I have two groups of electrons, okay, I now have one atom, okay, one bond my feet, one my head, and one my torso. What's that shape? A line. If I bend off axis, that means there's something causing me to bend. There's more electrons there. So it's still a line with just two groups. Okay? Most of those shapes become somewhat-ish obvious. I hate using the word obvious. Tetrahedral gets a little bit weird, okay? Because then we can't deal with a nice plane structure. We have to move into three-dimensional space.
I don't like that XC form.
That one was extra irritating, and I kind of apologize for that, but not really. Fair enough. Okay, join the club. There's 47 other people. After we look at our electron geometries, we then evaluate, well, what's going on with those electrons? Are they all the same? Well, if they aren't all the same, they're going to have different effects on the shape. That's where molecular shape then comes into play. So you're looking at two separate categories. Either way you do it, you still have to have a Lewis structure drawn out. You can't draw a Lewis structure, you can't do shape. Okay? So, play posit, I believed, had you draw CF4 and SO3. Do you want me to do either of those?
XEF4?
I will not do the xenon tetrafluoride. It's an extra tricky one. You can talk to me outside after class if you'd like me to do that one. So I listed some new ones, okay, that I don't think were covered in there. One of the things that pops up would say be single atoms, and this is usually where people get tripped up because they follow the textbook and then try and use these single atom comparisons as Lego bricks to build things. Because we understand Lego bricks. Molecules are not Lego bricks. That comparison is an awful, awful analogy. It destroys your understanding for future semesters. So if I was to look at carbon, this is the Lewis structure I want to deal with, just carbon. Rule 1, valence electrons. How many valence electrons? In the column it's in the fourth column, we get 4 valence electrons. Okay. This is where my rule falls apart, because I pick my center atom, well, it's only carbon, and I add electrons in pairs until I've achieved the total. Officially, for a single atom, we don't add them in pairs. We keep them unpaired first, and we'd end up with that configuration. The reason why textbooks like this is they can say, well, this is now a Lego brick where I can make a bond here, a bond here, a bond here, a bond here by adding an extra electron. That works great if that's the only thing you're doing. If you move to a more complex structure, that system turns into complete crap. Okay? Like a molecule. Okay? In some cases, it overlaps okay, some cases not. Let's take a look at CH4. Carbon has how many valence? 4. Hydrogen has how many valence? 1, but there's 4 of them. Total of 8 electrons. Carbon, hydrogen, 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 hydrogen. One of my recommendations that I'm working on trying to get myself to do is drawing a box around our center atom. Those of you saying, isn't hydrogen lower in electronegativity? It absolutely is, but hydrogen cannot bridge. It can only form one bond. So carbon must be the center atom. I will now...
Can never go in the middle.
Hydrogen can never go in the middle. Okay? Never.
Are there any other exceptions like that for what we're dealing with?
No.
Okay.
No. Yeah. Let's add the ish. Okay. So 8 electrons. I want to place those 8 electrons around the most electronegative element first, okay, in pairs. Carbon's the most electronegative, pairs. Notice where I'm placing these. I'm placing these between carbon and the other atom that's there. Okay, I'm not placing them over here. That's not the face of a square. I'm trying to keep it on the faces of a square. Okay. Everywhere I have a pair of electrons between atoms, I can convert into a line.
The line still means there's 2, right?
The line means there's 2 electrons in a bond. Okay. So you can see other rules where they try and do something else. The line is still ultimately 2 electrons, but I'm now trying to say that that is a bonding system, not just a pair of electrons.
Do you prefer the lines or the bonds or?
Lines. Okay, so that's why we go through and erase those. A lot of people don't like that because I'm making you draw more. Sorry. Okay, it works. Okay. Have we accounted for 8 electrons?
Yes.
2, 4, 6, 8. Yep, 8 electrons are in this structure. I need to satisfy octets. How many electrons around the carbon? 8. 2, 4, 6, 8. How many electrons around the hydrogen? 2. Is that 8? No. Is that hydrogen's octet? Yes. This is why it's not an exception to look at hydrogen with octets. It's in the first row. How many electrons can you fit in the first energy level? 2. Hydrogen's octet is only 2 electrons. Okay? Which means we now have our final structure. We'd be done. Okay? Shape. Are there electrons on this face? Yes. Are there electrons on this face? Are there electrons this face? Yep. 4 groups of electrons. 4 groups of electrons means tetrahedral. I then go through and, that says tetrahedral. I then go through and evaluate, are those groups of electrons different from each other? Okay? Or are they all representing the same thing? This is why bonds go as lines and things that aren't bonds stay dots. Are these all lines? Yes, which means they're all bonds. There's no difference between them. The molecular shape is also tetrahedral. 2 different questions with the same answer. Okay? I know, I apologize. Give me a second. NH3. Okay, we're going to get 8 electrons, trust me. Hydrogen, hydrogen, hydrogen. Okay. 2, 4, 6, 8. Okay. Whoops. Bond, bond, bond. Are there electrons? Yep. 4 groups of electrons. Shape is tetrahedral. Or electron geometry is tetrahedral. Are all of those groups the same? No, one's shown as dots. That allows me to differentiate. I have 1 non-bonding, 3 bonding. My answer for my molecular shape becomes trigonal planar. Sorry, pyramidal. And then, I know. Come back here. This is what I would recommend as an exam purge. Okay, it is the last slide in the slideshow. If you want to take pictures of it, you can. This is what you should memorize for at least the first 5 minutes of the exam. When you're told you can start, flip to the periodic table, identify this information. You no longer have to memorize it for the rest of the exam. Okay? Apologize for running late.